In module 2, we have looked into the generating function of the Legendre's polynomial along with some examples. In module 3, we will look into the recurrence relation of the Legendre's polynomial. Now, what is a recurrence relation? In mathematical sequence, when you derive a formula, sometimes it is easier that instead of expressing the nth term in terms of n, we try to express it in terms of the previous terms. That is what the recurrence formula is all about. Let us see how it works. Recurrence relations. So, what is a recurrence relation? In trying to find a formula for some mathematical sequence, a common intermediate step is to find the nth term not as a function of n, but in terms of earlier terms of the sequence. In mathematics, a recurrence relation is an equation that recursively defines a sequence or multidimensional array of values. A mathematical relationship expressing f n as some combination of f I with I less than n. For example, consider the recurrence relation x n plus 1 equal to r x n into 1 minus x n, which is also known as the logistic map. Let us take the example where you have to prove the recurrence relation n plus 1 p n plus 1 is equal to 2 n plus 1 x p n minus n into p n minus 1, where n is greater or equal to 1. To start the solution, we look into the generating function for Legendre's polynomial given by 1 minus 2 x z plus z square whole to the power minus half is equal to summation n equal to 0 to infinity z to the power n p n x, where mod x less or equal to 1 and mod z less than 1. Now, we differentiate this equation 1 with respect to z, and we will get minus half into 1 minus 2 x z plus z square to the power minus 3 by 2 multiplied by minus 2 x plus 2 z is equal to summation n equal to 0 to infinity n z to the power n minus 1 p n x, which is given by equation number 2. We now multiply 2 both sides by 1 minus 2 x z plus z square, and we get expression number 3. After simplification, we will get x minus z into summation n equal to 0 to infinity z to the power n p n x is equal to 1 minus 2 x z plus z square summation n equal to 0 to infinity n z to the power n minus 1 p n x, given by equation number 4. If we expand it, we will get equation number 5, which is nothing but multiplying each term of equation 4 by the respective summations. Then we equate the coefficient of z to the power n from both sides, and if you do that, you will see here the coefficient is p n x, here the coefficient is p n minus 1, here the coefficient is p n plus 1, here again p n, and here again p n minus 1. And if you put all these values, you will get equation number 6, which is x p n minus p n minus 1 is equal to n plus 1 p n plus 1 minus 2 n x p n plus n minus 1 into p n minus 1. After rearranging the terms, we will get the recurrence relation 1 as n plus 1 p n plus 1 is equal to 2 n plus 1 x p n minus n into p n minus 1. Let us come to the second recurrence relation, where you have to prove n p n is equal to x p dash n minus p dash n minus 1, where dash represents the first derivative of p n x. As usual, we take the generating function for Legendre's polynomial given by equation number 8. We differentiate 8 with respect to z, and we will get minus half into 1 minus 2 x z plus z square whole to the power minus 3 by 2 multiplied by minus 2 x plus 2 z is equal to summation n equal to 0 to infinity n z to the power n minus 1 p n x. If you simplify, you will get the equation number 10 from equation number 9. We again differentiate 8 with respect to x, and we get z into 1 minus 2 x z plus z square whole to the power minus 3 by 2 equal to summation n equal to 0 to infinity z to the power n p dash n x, given by equation number 11. We next multiply both sides by x minus z, and we will get z into x minus z into 1 minus 2 x z plus z square whole to the power minus 3 by 2, which is equal to x minus z summation n equal to 0 to infinity z to the power n p n dash x, given by equation number 12. After simplification, we will get equation number 14, which is z summation n equal to 0 to infinity n z to the power n minus 1 p n x is equal to x minus z summation n equal to 0 to infinity n z to the power n p n x, which is given by equation number 14. If you simplify this, you will get summation n equal to 0 to infinity n z to the power n p n x is equal to x summation n equal to 0 to infinity n z to the power n p dash n minus summation n 0 to infinity z to the power n plus 1 p dash n, given by equation number 15. We now equate the coefficient of z to the power n from both sides, and if you do that, you will get n p n from this term, n p dash n from this term, and n minus 1 p dash from this term, and you get the recurrence relation 2 as n p n x is equal to x p dash n minus p dash n minus 1, given by equation number 16. We next look into example 3, where you have to prove the recurrence relation 2n plus 1 p n x is equal to p dash n plus 1 x minus p dash n minus 1 x. We start with recurrence relation 1, which we have already proved, which gives 2n plus 1 x p n x is equal to n plus 1 p n plus 1 x plus n p n x. Now, we differentiate recurrence relation 1 with respect to x, and we get 2n plus 1 x p n x plus 2n plus 1 p n x is equal to n plus 1 p dash n plus 1 x plus n into p n minus 1, given by equation number 18. We now recall recurrence relation 2, which gives n p n is equal to x p n x minus p dash n minus 1. Now, we eliminate x p dash n x between 17 and 18, and if you do that, you will get 2n plus 1 into n p n x plus p dash n minus 1 plus 2n plus 1 p n x is equal to n plus 1 p dash n plus 1 plus n into p n minus 1 x. And if you simplify that, you will get equation number 21, which is our recurrence relation 3, which is equal to 2n plus 1 p n x is equal to p dash n plus 1 minus p dash n minus 1 x. We next look into example number 4, where we have to prove n plus 1 p n x is equal to p dash n plus 1 minus x p dash n. Now, please recall recurrence relation 2 given by equation 22, which says n p n is equal to x p dash n minus p dash n minus 1, and also recall recurrence relation 3, which is 2n plus 1 p n x is equal to p dash n plus 1 minus p dash n minus 1. Now, if we multiply equation 22 from equation 23, this is going to give recurrence relation 4, which is n plus 1 p n is equal to p dash n plus 1 minus x p dash n. example 5, where you have to prove the recurrence relation x square minus 1 p dash n is equal to n multiplied by x p n minus p n minus 1. Now, please recall recurrence relation 2 given by equation number 24, which is n p n x is equal to x p dash n minus p dash n minus 1. We multiply both sides by x and get equation number 25. Now, recurrence relation 4 gives n plus 1 p n x is equal to p dash n plus 1 minus x p dash n. We replace n by n minus 1 in equation number 26 and we get n p n minus 1 x is equal to p dash n minus x p dash n minus 1. We next subtract 26 from equation number 24, and if you do that, you will get n x p n minus n p n minus 1 equal to x square minus 1 p dash n plus 1. If you rearrange the term, we arrive at recurrence relation 5, which is x square minus 1 p dash n is equal to n multiplied by x p n minus p n minus 1. Our next recurrence relation given by example 6, which is 1 minus x square p dash n is equal to n plus 1 multiplied by x p n minus p n plus 1. We start with recurrence relation 1, which says 2n plus 1 into x p n, which is equal to n plus 1 p n plus 1 plus n p n. Next, we write this 2n as n plus n, and we get the term n plus 1 into x p n is equal to n plus 1 p n plus 1 plus n p n. We open the bracket and we will get n x p n plus n plus 1 x p n is equal to n plus 1 p n plus 1 plus n p n. Rearranging the terms, we will get equation number 28, which is n x p n minus n p n is equal to n plus 1 p n plus 1 minus x p n. Now, please recall relation recurrence 5, which is x square minus 1 p dash n is equal to n times x p n minus p n minus 1. We simplify, we substitute n p n minus n p n from equation 28 here to get the recurrence relation 6, which is x square minus 1 p dash n is equal to n plus 1 p n plus 1 minus x p n, which is our recurrence relation 6. In example 7, we have to show in the first part that p n plus 1 minus p n minus 1 divided by 2 n plus 1 is equal to integration p n dx plus a constant c. To do that, we take the recurrence relation 2 n plus 1 p n is equal to p dash n plus 1 minus p dash n minus 1, and we can express it in the form given in equation 29, which is p n x is equal to 1 by 2 n plus 1 d dx of p n plus 1 minus p n minus 1. If we integrate 29, we will get on the left hand side integration p n dx plus the integrating constant c is equal to 1 by 2 n plus 1 multiplied by p n plus 1 minus p n minus 1, which is the proof of the first part of this example. In the second part, we have to integrate 29 with respect to x from x to 1, and we will be getting integration x to 1 p n x dx is equal to 1 by 2 n plus 1 p n plus 1 x minus p n minus 1 x from x to 1. If we integrate this and simplify, we will get p n minus 1 x minus p n plus 1 x divided by 2 n plus 1, because p n plus 1 and p n minus 1, both the values is equal to 1, and 1 minus 1 gives you 0. In example 8, we have to show 2 n plus 1 x square minus 1 p dash n is equal to n into n plus 1 p n plus 1 plus p n minus 1. Please note, recurrence relation 5 gives x square minus 1 p dash n is equal to n times x p n minus p n minus 1 given by equation 30, and recurrence relation 6 gives x square minus 1 p dash n is equal to n plus 1 p n plus 1 minus x p n given by equation 31. Multiplying 31 by n plus 1 and 30 by n and adding, we will get n plus 1 x square minus 1 p dash x plus n into x square minus 1 p dash n is equal to n plus 1 into n multiplied by x p n minus p n minus 1 plus n into n plus 1 multiplied by p n plus 1 minus x p n given by equation 32. If we simplify this, we come to the desired result, which is 2 n plus 1 x square minus 1 p dash n is equal to n into n plus 1 p n plus 1 plus p n minus 1. In example 9, we have to show p dash n plus 1 x plus p dash n is equal to p 0 plus 3 p 1 plus dot dot 2 n plus 1 p n. Recall recurrence relation 3, which is 2 n plus 1 p n is equal to p dash n plus 1 minus p dash n minus 1 given by equation 34. We replace n by 1, 2 dot 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 n minus 1 in 34, and we will obtain 3 p 1 is equal to p 2 dash minus p 0 dash, 5 p 2 is equal to p 3 dash minus p 1 dash, 7 p 3 is equal to p 4 dash minus p 2 dash, and so on. If we now add all these expressions, you will see that this p 2 dash cancels with this p 2 dash, this p 3 dash cancels with this p 3 dash, and so on. So, if you add them, you will get the ultimate result as 3 p 1 plus 5 p 2 plus 7 p 3 plus dot dot 2 n plus 1 p n is equal to minus p dash 0 minus p 1 dash plus p dash n plus p dash n plus 1 given by equation number 35. Since we already know that p 0 x is 1 and p 1 x is x, clearly p dash 0 is 0 and p 1 dash is equal to 1, which I can write as p 0 x. We substitute these values in 35 and we will get 3 p 1 plus 5 p 2 plus 7 p 3 plus dot dot 2 n plus 1 p n is equal to 0 minus p 0 plus p dash n plus p dash n plus 1 given by equation number 36. If we rearrange the terms, we will get our desired result as p 0 plus 3 p 1 plus 5 p 2 plus 7 p 3 plus dot dot plus 2 n plus 1 p n is equal to p dash n plus p dash n plus 1. In our next example, we have to show x p dash n is equal to n p n plus 2 n minus 3 p n minus 2 plus 2 n minus 7 p n minus 4 plus dot dot dot. We take the help of recurrence relation 2 and 3 given by 38 and 39, which is 7 p n is equal to x p dash n minus p dash n minus 1, and recurrence relation 3 gives 2 n plus 1 p n is equal to p dash n plus 1 minus p dash n minus 1. We next replace n by n minus 2, n minus 4, n minus 6 in equation number 39, and we get p dash n minus 1 minus p dash n minus 3 is equal to 2n minus 3 p dash n minus 2. P dash n minus 3 minus p dash n minus 5 is equal to 2n minus 7 p dash n minus 4, and so on, which is given by equation 40. We add all these terms, and if you do that, you will see that this cancels with this, p dash n minus 5 cancels with p dash n minus 5, and so on, and we get the result x p dash n is equal to n p n plus 2n minus 3 p n minus 2 plus 2n minus 7 p n minus 4 plus dot dot dot, which is our desired result. So far, we have seen the recurrence relation and its proof of the Legendre's polynomial or Legendre's function of first kind. We next move to the recurrence relation of Legendre's function of second kind. Please note, since Legendre's function of second kind is an infinite series, you have to be very careful in its calculation. We next look into the recurrence relation of Legendre's function of second kind. Before that, we need three results, which are result 1 given by q n x is equal to 2 to the power n into n factorial divided by 2n plus 1 factorial summation r equal to 0 to infinity n plus 2r factorial x to the power minus of n plus 2r plus 1 divided by 2 to the power r into r factorial 2n plus 3 2n plus 5 dot dot 2n plus 2r plus 1. Our second result 2 is just the differentiation of q n x, and we replace n by n minus 1. The result 3 is we again differentiate q n and replace n by n plus 1, and we will get q dash n plus 1 x is equal to minus 2 to the power n into n factorial divided by 2n factorial multiplied by summation r equal to 0 to infinity n plus 2r plus 2 factorial x to the power minus n plus 2r plus 3 divided by 2 to the power r into r factorial multiplied by 2n plus 1 2n plus 3 dot 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 2n plus 2r plus 3. We will be using these results 1, 2 and 3 in the proof of the recurrence relation of Legendre's function of second kind. The first example, we have to show that q dash n plus 1 minus q dash n minus 1 is equal to 2n plus 1 q n. We take q dash n minus 1 plus 2n plus 1 q n, where we substitute the values of q dash n minus 1 and q n from result 1 and result 2. And if you do that, you will get equation number 42. After simplification, we get equation number 43, which is 2 to the power n into n factorial divided by 2n factorial multiplied by summation r equal to 0 to infinity n plus 2r factorial x to the power minus n plus 2r plus 1 divided by 2 to the power r into r factorial into 2n plus 1 2n plus 5 dot 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 2n plus 2r plus 1 minus summation r equal to 0 to infinity n plus 2r x to the power minus n plus 2r plus 1 divided by 2 to the power r factorial 2n plus 1 2n plus 3 dot 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 2n plus 2r plus 1. Further simplification gives equation number 45, which is 2 to the power n into n factorial divided by 2n factorial into summation r equal to 0 to infinity minus 2r n plus 2r factorial x to the power minus n plus 2r plus 1 divided by 2 to the power r into r factorial 2n plus 1 2n plus 3 dot dot 2n plus 2r plus 1. We substitute r by s plus 1, and if you do that, you will be getting minus 2 to the power n into n factorial divided by 2n factorial summation s equal to 0 to infinity n minus 2s plus 2 factorial x to the power minus n plus 2s plus 3 divided by 2 to the power s into s factorial into 2n plus 1, 2n plus 3 dot dot 2n plus 2s plus 1, and which is equal to q dash n plus 1 by result 3. Our final recurrence relation, we have to prove 2n plus 1 x q n is equal to n plus 1 q n plus 1 plus n q n minus 1. To start the proof, we take the expression n q n minus 1 minus 2n plus 1 x q n. We substitute the values of q n minus 1 and q n from result 1, and if you do that, you will be getting equation 50. After simplification, we will get equation 52, which is 2 to the power n into n factorial divided by 2n plus 1 factorial summation r equal to 0 to infinity n plus 2r minus 1 factorial x to the power minus n plus 2r divided by 2 to the power r into r factorial multiplied by 2n plus 3, 2n plus 5 minus dot 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 2n plus 2r plus 1 multiplied by n into n plus 2r plus 1 minus 2n plus 1 n plus 2r, given by equation 52. Further simplification, we will get equation 54, which is 2 to the power n into n plus 1 factorial divided by 2n plus factorial multiplied by summation r equal to 1 to infinity n plus 2r minus 1 factorial x to the power minus n plus 2r divided by 2 to the power r minus 1 into r minus 1 factorial 2n plus 3, 2n plus 5 dot 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 2n plus 2r plus 1. Please note, here it is 2 to the power r and here it is minus 2r. This minus 2r and 2 to the power r into r factorial, they get cancelled and going to give you 2 to the power r minus 1 into r minus 1 factorial, and that is why the summation is from r equal to 1 to infinity. We replace r by s plus 1 and we will get equation 55, which is equal to minus of n plus 1 2 to the power n into n factorial divided by 2n plus 1 factorial, which is summation s equal to 0 to infinity n plus 2n plus 1 factorial x to the power minus n plus 2s plus 2 divided by 2 to the power s into s factorial 2n plus 3, 2n plus 5 dot 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 2n plus 2s plus 3. If we simplify it further, we will get equation 56, which is minus of n plus 1 2 to the power n n plus 1 factorial divided by 2n plus 3 factorial multiplied by summation s equal to 0 to infinity n plus 2s plus 1 factorial x to the power minus n plus 2s plus 2 divided by 2 to the power s s factorial 2n plus 5 dot 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 2n plus 2s plus 3, and which is equal to minus of n plus 1 q n plus 1, which we can get from result 1. If we rearrange the term, we will get equation 58, which is 2n plus 1 into x q n is equal to n plus 1 q n plus 1 plus n q n minus 1, which is our desired result. In this module, we have learned about the recurrence relation of Legendre's polynomial and Legendre's function of second kind. Please note, this module is calculation oriented, and hence I advise you that you take a paper and a pen and do the calculation yourself as you go through this module. In our next module 4, we will learn about the orthogonal properties of the Legendre's polynomial and Rodricks formula. Thank you.